Today we'll be considering question 7, which reads as follows. The addition and multiplication of cardinal numbers are defined by the cardinality of A plus the cardinality of B is equal to the cardinality of A disjoint union B, and the cardinality of A times the cardinality of B is equal to the cardinality of A Cartesian product B for any sets A, B, where they are finite or not. Our goal is to show that n plus aleph null is equal to aleph null plus aleph null is equal to aleph null for any n in the natural numbers, and then show that the product of aleph null times aleph null is equal to aleph null. Take a couple seconds to try this out for yourself, then we'll do some hints, then we'll get on with the proof. Alright, for this problem some hints are that we're going to recall that to show that some things are equal, we need to show that there are bijection between the sets underlying them, in the sense that to show that the cardinality of some sum is equal to the cardinality of another set, we need to show that there's a bijection between the set and the other set. So we'll do that actually for both these problems, and that'll be a very useful result. An additional hint might be that if you want to prove something for any n, then you might want to prove it for all n, and that will lead you down a particular kind of proof. Alright, let's begin. So since we're trying to prove for any n, let's prove for all n, and then we can come back and say, oh, so our choice of n was arbitrary. Alternatively, you could try to prove this for any arbitrary n, but I think it's more in the line of what they wanted you to prove by doing it for all n. So let's begin. First, we'll prove the somewhat easier but scarier product of this, where we'll eventually get equality with this by showing that this left term is equal to aleph null itself. So let's prove that aleph null plus aleph null is equal to aleph null. Well, aleph null plus aleph null is the representation of the cardinality of the natural numbers plus the cardinality of the natural numbers. And we know this can be equal to the cardinality of the natural numbers disjoint union with the natural numbers. I'll note that since we're taking a disjoint union, we are going to want to index these as the natural numbers 1 and 2. So we just need to now show a bijection between the natural numbers disjoint union, the natural numbers, and the natural numbers themselves, and then we'll have the equality we want to find. So you can think about this for a second, and essentially if you ever want to prove a bijection with the natural numbers, it's always a good idea to list them out. So if we have the natural numbers 1 union the natural numbers 2, a natural way to index these is 1, 1, where 1, 1 means 1 taken from the first set of natural numbers, 1, 2, 2, 1, 2, 2, so on and so forth. And we'll see that this seems to be a pretty strong way of listing all of them out. So let's use this as a representation to show this is actually bijection. And in this case, we'll take the ith element of this product, and of this disjoint union, and we'll send it to 2i or 2i minus 1. And the conditions are if I is an element of the natural numbers 2, and this is if they're from the natural numbers number 1. That is, let's take any element of the set. So let's take this first element, for instance. That's I from natural numbers number 1, and it's going to send it to the first element. Therefore, we're going to get I1. Or we're going to get 1, 1 in the first position. Then we'll do 1, 2, which will be sent to the second position, because it's 2 times I, and I is 1. Therefore, we send that to I2. And in this way, we begin to associate them. Now we just need to prove that this is a bijection. So surjection is easy. First, we'll note that it's surjective because for any natural number n is either even or odd. So let's just do the even case, but the odd case is exactly identical. If it's even, then it can be written as 2 times I uniquely. And then we simply say, oh, this is covered by the element I, where I is taken from n2. And therefore, we have it covering, and the odd case is exactly the same for this one. Next, let's prove it's injective, and that's kind of by construction. Let's take any 2 unequal elements. Let's call them I and j. There are 4 cases. Either they're from the same sets, in which case clearly they're sent to different sets since 2i minus 1 is injective, or 2i is injective. Next, if they're from different sets, then clearly they're going to be from different sets because 2I does not equal 2j minus 1 for I comma j being taken from the natural numbers. Therefore, we have shown that this is a surjective and injective function, therefore it's a bijection, and we have a complete, and for bijection, therefore we have the equality that aleph null plus aleph null is equal to aleph null for any n in the natural numbers. It doesn't matter, since we're not taking n from the natural numbers. Now let's do the n proof, as a matter of fact. And for this, we're actually going to prove that this is true for all n. So to prove that it's true for all n in the natural numbers, we'll do proof by induction. So let's note that we'll prove that 1 plus aleph null is equal to aleph null. And then we'll prove the induction step. So to prove the base case, we simply send the element. So from this product, this is the disjoint union of 1 disjoint union with aleph null. And in this case, we'll send this one to the first element. So 1 gets sent to the natural number 1. And then we'll send n in these natural numbers to the successor of n, and we'll just denote that as n plus 1 for now. Actually, no, not the successor of n, because, that's fine, because we're allowed to use 1. So we're going to send n to the successor of n, or n plus 1, and now we just need to show that this covers. So the way we do that is by saying n plus 1, the successor operation is true for all elements. All elements have a pre-successor, except for 1, and in this case we've shown, so that means that this covers all elements of the natural numbers except for 1 in the goal space. Sorry, that should be, in the natural numbers. So this covers everything except for 1, and then this element clearly covers 1, so we're surjective. And then we'll note that that is injective in the sense that no two elements have the same successor. Therefore, none of these elements will match the same thing. And then we'll note that no element has 1 as its successor in the natural numbers, so none of these elements will hit 1, except for now we've added this element. I'll call this maybe 1, 1, to denote that it's different from 1 in the natural numbers. And then we'll see that this covers 1. Therefore, unequal outputs come from unequal inputs. With that, we've shown it's injective and surjective, therefore it's a bijection, so we have our base case. Next, let's assume that for the general case of n plus 5n, for n naught, then we'll assume that there exists a function phi of k which takes the element k and sends it to a natural number, let's call it m, and we have that 5k is bijective. That means it's surjective and injective. Next, it's pretty easy to see. Next, we'll do the induction step. So let's try to prove that n plus 1 plus aleph null is equal to aleph null. So we need to prove there's a bijection between the set of the first n elements. Let's call that A. Discrete union with the natural numbers, where this has n plus 1 elements, and this, of course, has aleph null elements, where the natural numbers, of course, have aleph null elements. So we have a bijection for for the first n elements of this. So therefore, we're going to make a new map. We'll call it, let's call it psi, which takes 1 and sends it to 1, where 1 is taken from this. So I'll call it maybe 1, 1, and sends it to 1 in the natural numbers. And then it takes the nth, that's wrong. It should take n plus 1, the new element that we do not have a map for, takes n plus 1 to 1, and then takes any other natural number, takes any other element in this sum. It takes it, and let's call that k again. Takes the element k and sends it to 5k plus 1. Here's our psi, and this is our proposed psi, and now all we need to do is prove that it's a bijection. So we'll first note that 5k was surjective before. When we shifted up 1, we no longer have a covering of the element 1, except with n plus 1, being sent to 1, we do have a covering. So this new map psi is surjective. Next, we'll prove that psi is injective. Since 5k was injective, we know that phi of k plus 1 is going to be injective. And finally, we'll note that we send n plus 1 to 1, which is not equal to the output of any other number, since that range of 5k was the natural numbers. So the range of 5k plus 1 is the natural numbers shifted over by 1 unit. Therefore, we have that this set is injective because it sends unequal elements, i.e. recall that k is taken from a union natural numbers, or from this disjoint union except for this element n plus 1 in A. So that since k, no two k elements will ever be equal because 5k is injective, so 5k plus 1 is injective. N plus 1 is clearly not going to equal any of those because k gets sent to a non-1 element and n plus 1 gets sent to a 1 element. Therefore, they have the different outputs for different inputs. And of course, n plus 1 will equal n plus 1, but that's okay for injective functions. Fantastic. We've proved it for the base case of n equals 1, and then we've shown that n implies n plus 1. Therefore, by induction, we know that our equality that n plus aleph null is equal to aleph null for all n. Therefore, now that we've proven this induction, we've proven for all n in the natural numbers. Therefore, it's true for any n in the natural numbers. And by the transitivity of this kind of equality, we show that phi of n of aleph null is equal to aleph null plus aleph null is equal to n plus aleph null. Another way of saying that is we could simply have used the bijections that we constructed in each of the previous proofs to show that the bijection between aleph null and aleph null plus aleph null is equal to n plus aleph null, since we can construct a bijection between them. So the cardinalities of those, or rather that sum is equal. Fantastic. Now that we've proved the first part of the problem, let's proceed with the second part of the problem, which as we've read is the product of aleph null times aleph null. Of course, we're going to proceed in a very similar way, which is that we need to just simply construct a bijection between A cross B, but in this case, A and B are simply going to be the natural numbers. So we get natural numbers. We'll call it 1. Cartesian products with the natural numbers 2, and we'll just draw this out to give us some elucidating information. Let's let the first element of the natural numbers 1 be on this top row, so we'll call this 1, 2, 3, and so on. And from natural numbers 2 is from this column. So for instance, we get the element of the Cartesian product 1, 1 here. Here's 2, 1. Here's 1, 2. Here's 2, 2. And this is up to a transpose of this kind of matrix, and so on and so forth. And now we simply need to construct a bijection between this set and the natural numbers. And looking at this, we begin to see where we might be going. And in fact, it is simply that we are going to have we're going to apply Cantor's diagonalization argument in the sense that we'll let this be the first element. Here's the second element and the third element. Here's the fourth, fifth, and sixth elements, and so on and so forth. Clearly, this is going to be surjective since we cover 1, 2, 3, 4, 5, 6. And for any element, we can construct, for any element n in the natural numbers, it's pretty interesting to construct the element in this. It's interesting to solve for the functions I of n and j of n, but they're not terrible to solve for. And once you do that, you see that the ijth element corresponds to n, so every n element is covered by some ij element of this Cartesian product. Therefore, it's surjective. Next, let's just index injectivity. And that kind of follows from this proof in the sense that if you have the different outputs, that is n and m, then I of n and j of n will be unequal. That is, you can also prove this by saying that you have unequal outputs. You have equal outputs, and you'll see that these I of n and j of n functions are unique. Or you can simply just check that. You can simply check that, it's well known that this is you can think of this as a finite union. Of a countable union of countable sets, in the sense that this is the first set, here's the second set, here's the third set, and there are countably many of these. And so if you union all, and then each of these sets is countably long in the sense that it's 1, 1, 1, 2, 1, 3, etc. And therefore you just apply counter-diagonalization and say that this is countable. And so saying that it's countable means there's a bijection. So implicitly you have that bijection that way. With that, we will note that we are, we'll note that we're done because we have proven that there's a bijection between these. So we've shown that the product aleph null times aleph null is equal to aleph null. With that, we are done, and thank you for watching.